Welcome all to today's webinar. In this webinar, we will showcase how our groundbreaking new technology, Aspen Hybrid Models, will enable you in the energy industry to leverage the power of artificial intelligence to overcome challenges that could not be addressed before using conventional simulation technology. My name is Sandeep Mohan. I'm the Product Marketing Manager for AspenTech's engineering solution in refining and heat exchanger design. I've been with AspenTech for over 8 years, prior to which I worked as thermal engineer in the EPC industry. Our speaker today is Alex Rayo, Product Manager for Aspen Hybrid Models. Alex is our expert in Aspen Hybrid Modeling that brings together artificial intelligence technologies with first principles-based simulation technology. Alex has been with AspenTech for over 7 years. Alex has an undergraduate degree in chemical engineering from the University of Massachusetts, Amherst. Here is the agenda for today's presentation. We will start with introducing the latest Aspen Hybrid Modeling technology and other innovations with our latest version 12 solution that was released last month. We will then move to describe the hybrid modeling technology, followed by 2 demonstrations of how you can use the technology to address 2 real-world challenges. We will then summarize the key points of the webinar and open the forum for questions. You need not wait till the end to post your question. We encourage you to post your questions anytime during the webinar session. Let us start with the introduction. Our latest version 12 solution, released just last month, is set to truly revolutionize the process industry. With this release, we have unleashed the power of artificial intelligence to the process engineering community. We did this by embedding AI to our solutions, so our users wouldn't have to do the same. This is truly democratizing the application of artificial intelligence, so users of all skill levels can leverage it to solve complex problems that could not be solved easily using conventional simulation technology today. This capability has aroused tremendous excitement amongst our user community worldwide and amongst technology analysts globally. This release is a major step in our journey towards delivering self-optimizing plants. We have a number of game-changing new capabilities in V12 in addition to the AI-based Aspen hybrid models. We will, of course, be elaborating more on the AI-based hybrid modeling through the rest of this webinar. The other major innovations include Aspen Multi-Case, which will now enable users to run thousands of case studies simultaneously, thereby help drive optimal performance of their plants by analyzing all possible operating scenarios, as well as to help develop most optimal designs by analyzing thousands of design alternatives. The next innovation is ACCE Insights. This is set to significantly improve the area of cost estimation, helping users across a company understand better their project estimates through quick visualization. And additionally, it enables multiple disciplines to collaborate better within the company and with their clients. In short, the solution ensures every cost estimate a company makes is better than the previous cost estimates they have made. The next major innovation has to do with the deployment of online digital twin solution. V12 enhancements automates much of the workflow involved in deploying Aspen HYSYS digital twin models online. The users can deploy models online from within the Aspen HYSYS environment. By the way, this is also true for Aspen Plus users. Another revolutionary capability is the in-context guidance that provides users access to best practices and tips and tricks that are relevant and helpful to the specific task that a user is trying to accomplish from within Aspen HYSYS or Aspen Plus. This, we believe, will help further accelerate competency development for our users. And again, these are just few of the innovations. There are very many in the V12 release. Now, let us take a quick look at few of the challenges faced by the process industry. One key challenge is the ever-increasing need for greater collaboration between the dispersed workforce and need for better information sharing between design and operations. There is growing pressure on productivity from increasing market volatility. Now, these two challenges, of course, have heightened further with the pandemic. Another major challenge for the industry is the impending loss of knowledge and experience as a large segment of the senior operations staff retire from the workforce. And finally, there is the increasing challenge of maintaining competitive edge while achieving sustainability goals. These long-term and short-term challenges can be effectively addressed by harnessing the power of artificial intelligence. And AspenTech's approach to enabling you to leverage this power is by embedding artificial intelligence in our solution so you wouldn't have to do it yourself. These solutions use the data from across your processes and assets and then applies a combination of data insights techniques and domain expertise to deliver deeper insights into your processes, give guidance for better decision making, and automate your workflows. By data insights, we mean various machine learning and advanced analytic technologies. Domain expertise involves first principles engineering and about 40 years of AspenTech's real-world expertise in solving process engineering challenges. This results in a fit-for-purpose, domain-specific AI-enabled application that really delivers measurable returns. And this is really what we mean by industrial AI. Now, how are we delivering this industrial AI to you? And this is through this brand new Aspen hybrid model offering. This solution combines the power of artificial intelligence, the fundamental first principles engineering, and about 40 years of AspenTech's domain expertise to enable users to simulate processes and equipments that they were not able to simulate before using conventional simulation technology. This enables modeling of diverse processes that are complex and difficult. It enables engineers of all skill levels to build models. It facilitates improvement of model accuracy using machine learning without requiring the user to have any AI expertise. More importantly, it tremendously reduces the effort required in maintaining the accuracies of these models, so the models are valid for a longer period of time. Now, let us take a deeper look into what really are these new Aspen hybrid models. One good way to understand the hybrid model is to first look at the conventional pure first principles based models. First principles meaning models built based on the fundamental physics and chemistry of the process. These refer, of course, to the conventional process simulation technology. As we all know, this technology requires some expertise to use them and requires some time and effort from the user to create models. In certain cases, they may also prove to be insufficient in modeling certain niche or complex processes. Now let us look at the pure machine learning based models. Now these models, on the other hand, require tremendous amount of good data. Unlike first principle based models, pure machine learning based model predictions may not conform to real world physical constraints and principles of mass and energy balance. In some cases, these models may also be hard to interpret. Now, this is where hybrid models come, combining the best of the other two modeling technologies. It brings together AspenTech's decades of domain knowledge, the first principles-based modeling techniques, and at the same time, it brings in the machine learning and AI technologies to overcome the limitations of conventional simulation technologies. So this is how hybrid models enable development of self-sustaining fit-for-purpose models that can be used with confidence across an asset's lifecycle. In V12, we are enabling users the option to develop two types of hybrid models. The first one is what we call reduced order models. Now, as depicted in this slide, the models use simulation data derived from simulation models in either Aspen HYSYS or Aspen Plus to build machine learning models that are guided by AspenTech's domain knowledge and constraints such as mass balance checks. These reduced order models have the required agility that makes them perfect for deploying them in Aspen HYSYS flowsheets, for developing plant-wide digital twins, or developing accurate nonlinear planning models, which can be deployed in Aspen PIMS-AO. The second type of hybrid models are what we call AI-driven hybrid models. These models can take in data from a variety of sources, such as operations data, lab data, pilot plant data, or simulation data. Now, like before, this data is used to develop machine learning-based models that are guided by AspenTech's domain knowledge and constraints such as mass balance checks. Now, in addition, these models can leverage first principles to compute parameters so that it can augment the data pool. These models are ideal for deployment in Aspen HYSYS flowsheets for simulating complex processes that cannot be otherwise simulated today using conventional simulation technologies. They can help as inferential sensors for properties that cannot be predicted by process simulators. And more importantly, they can be used as digital twins for operational distance support. Now, as you may have inferred by now, Aspen hybrid models deliver deeper insights into both processes and equipments using the power of AI, which is not otherwise possible using conventional simulation technology. There are very many real-world use cases where this technology can help you significantly. This includes accurate and robust reduced order models for both engineering and operation support. They can help develop non-linear reduced order models that could be used for updating your refinery planning models. And as I said before, they can act as virtual sensors for KPIs. And most importantly, they can help develop robust, large-scale site-wide models. Now, due to the limited time we have for this webinar session, we will only be able to demonstrate today the reduced order hybrid models. However, we did do a detailed demonstration of the AI-driven hybrid models in a webinar conducted last week for the chemicals industry. So we will leave web links to the recording of that webinar in this deck. So when we send this deck to you after this webinar, you can click on that link and watch the demonstration. Also, we will be demonstrating the AI-driven hybrid models in our upcoming webinar in December. So please do look out for our invitation for that webinar. Now, with that, I will hand over this presentation to Alex Rayo. Alex, over to you.
All right. Thank you very much, Sandeep. So as Sandeep said, we'll be showing you two different demonstrations today, both focused on this reduced order hybrid model type. So before we jump into the demo, just want to cover a few pieces to give you a little bit more context. So really what we're looking to do behind this reduced order hybrid modeling concept is to create a more accurate and more robust model as a result. And by doing this, we can help to increase the speed in using these in digital twin type applications in engineering, as well as operation support, and then as you'll see in our second demo, within the planning world as well. So we can take these reduced order models and build them based off of existing simulation models so that we can simplify models of existing oil and gas facilities to really enable a more maintainable and more accurate model as a result. Now, we can have these models that run more quickly, are more robust, and are more overall performant that allow us to perform more frequent and faster optimization problems, and also look at optimization problems over a much wider and larger scale. We can take these reduced order models and easily deploy them on different endpoints, including what you'll see today in the simulation world, but also we could think about deploying these into the online applications as well. And they're very easy to use and simple to use models. So we can use them for our traditional users. We could deploy them down to folks who don't have a high level of expertise in the simulation world. And as you'll see, they're very easy to build and very easy to maintain and utilize within the tool itself. So for this given application, we worked with a number of different companies, and this is just a sample of some of the work we did with a large American multinational company, an energy company. And the challenge they were facing was there was a significant amount of effort needed to calculate all of these different gas allocation calculations. It's a very complex model. It takes significant time to solve, and it required a very high level of expertise to do this kind of work. And overall, they were trying to reduce some of their energy use and improve the overall sustainability. So the solution we came up with was a reduced order hybrid model for the dehydration section within Aspen HYSYS. So we built a reduced order model that could be deployed back into the engineering case. And as a result of this, we were able to save about $500,000 a year in total effort required for performing these gas allocation calculations. And we gain an even further benefit of this by allowing this process to occur more frequently. And since this is a very streamlined, automated, and relatively easy workflow, we can do this type of activity really as frequently as we like. And this underlying reduced order model is 10 times faster than the initial simulation case, and it's also more robust. So you get additional benefits through that aspect as well. Now, the workflow for actually building these, which I'll show you in the product in just a minute, starts first with the data collection and the data definition. So what we're ultimately doing is building a reduced order model based off of an existing simulation case. And in order to build that reduced order model, we first need to have a data set that represents the full operating range that I really want that model to represent. Now, we could generate that data in a number of different ways. We could take our existing simulation model and run it through, for example, the case study in HYSYS. We could potentially use ASW or other tools. However, we have a brand new product called Aspen Multicase that makes this process very, very simple and a lot quicker and a lot more straightforward. So I'll show you what that looks like in the tool. But what Multicase allows us to do is not only perform this in a more streamlined and easy manner, but also take advantage of high-performance computing, run these different cases in parallel, and also helps to set up an intelligent design of experiments to make sure that for the range that I define, I'm really getting adequate representation and sequencing the cases in a very efficient and in a very intelligent manner so that I can do this analysis as efficiently as I possibly can. Now, once this data definition and collection is complete, I can take that model, or all of that data, into my AI model builder to perform the hybrid model building steps. So the Aspen AI Model Builder is our brand new product we just released with version 12 that allows really the building, the data cleaning, the validation, and everything else needed to build and eventually deploy one of these hybrid models. So as you'll see in the demonstration today, the AI Model Builder is actually a SaaS application hosted on the Aspen Cloud that you log into going to aimodelbuilder.aspentech.ai, and you have all of the features and functions within that tool to build and deploy these hybrid models. Once we finish the model building and the model validation step, we can then begin the process of exporting this model and deploying it into a given end product. So here we'll be using this model within Aspen HYSYS, but you could also think about using this model perhaps in Aspen Plus or online, or as you'll see in another demonstration, how we can also deploy it into the planning world. So the demonstration that I will show you today is a case where we can build a reduced order model for a gas plant, specifically focused on the gas dehydration section. So we can take a large portion of the HYSYS flow sheet and simplify it down into a form that we build it in a reduced order model and deploy it right back into the simulator. That again allows us to improve the overall performance, stability, and robustness of the model as a result. So with that, I will transition over to the demo and show you what we actually do to build one of these models. Okay, so what you're seeing here is a HYSYS model of a gas plant, and I'm specifically focused in on this gas dehydration, compression, and NGL recovery section. So what we're actually going to do is build a reduced order model that represents the full scope of the simulation case that I'm showing you here. So all of these distillation columns, streams, heat exchangers, pumps, compressors, everything you see contained in here will be simulated by that one single reduced order model. Now to make things a little bit easier, if I go back to my parent flow sheet here, I have everything contained within this flow-1 subflow sheet. So everything you see in here is within that subflow sheet, which will make things much easier when I get over to Multicase for actually generating this data. Now, I'll go over to Multicase and we can begin the process of generating all of the data that we need to build our reduced order model. So what I'm showing you here, this is Aspen Multicase. And Aspen Multicase has a web-based interface, but it is a desktop product. This is installed locally on your machine. And what we can see here is I have a number of different options available to me, including case study, reduced order model, and multi-file analysis. Now in this case, I'm going to be focusing on the reduced order model, and I've already set up this configuration just in the interest of time, but I will show you what the overall process looks like and really what's involved with building one of these reduced order models. So I'll go ahead and click on my gas plant reduced order model file here, and you'll see I have a scenario created within here. And what this scenario has is all of the independent and dependent variables that I care about for my particular reduced order model. And multi-case makes this really, really easy to set up. So I'll show you the actual process of doing this. You would first create a new scenario and then choose a focus for your reduced order model. Now, if you recall in that HYSYS case, I was saying that that entire section of the flow sheet I want to focus on is contained within that flow-1 sub-flow sheet. So within multi-case, all I need to do is click this button here to select an equipment and select my flow-1 as my focus. And after I do that, this entire grid within multi-case is automatically populated with all of the independent and dependent variables I need to build my reduced order model. So what we've done is automatically selected the minimum equations or the minimum variables, needed to build this reduced order model. I have all my temperatures, my pressures, flows, and compositions on all of my boundary streams. I have the option of adding more variables if I want to, if I wanted to include anything within the internals of that subflow sheet or perhaps other types of specifications on these streams or units. But right now I have all the information I need to build this model. So again, I've already run this on my actual machine, again, just in the interest of time. But if I open up this monitor form here, you can see I ran about 1,000 cases, and this took just over 12 minutes, which is an enormous improvement by using this multi-case technology. So I mentioned briefly that multi-case allows us to take advantage of high-performance computing, and we can also run all of these different simulation cases in parallel after I've set up my lower and upper bounds. Within this configuration menu here, I have options of setting how many parallel runs I want to do. Of course, this is determined largely by the number of CPUs I have available. This is just running on my laptop, so I have a quad-core CPU here, 4 CPUs. But you could also envision using this on a more powerfully spec'd machine, desktop, or even a server, and you can really achieve very, very quick results executing thousands of simulation runs. Now, once this is complete, I can export all of this data from multi-case and begin the process of building this hybrid model within the AI Model Builder. So I'll switch over to my other tab here, which is the AI Model Builder product. Now, as a reminder, this is a SaaS product that lives on the Aspen Cloud. So AspenTech hosts all of this software, and you simply log in and use it using your unique set of credentials. So I would navigate to aimodelbuilder.aspentech.ai, and I would begin the process of building my hybrid model. So again, in this case, I've already set up this configuration, but I'll walk you through the process of the different steps involved so you can see how simple and straightforward it is to truly build one of these reduced order models. So I've gone ahead and opened one of my projects, and I want to point out a few things along the way. So what you'll see within the product here is we have a step-by-step workflow up along the top, starting first with import data, followed by manage variables, clean data, build model, and then lastly validate the model. So these are the 5 different steps I need to follow to successfully build this hybrid model. So what I would do is I would first on the import data page, of course, upload the data that I just exported from multi-case. I've already done this, so I'll go ahead and proceed to the next step. And then we're brought to a manage variables page. And on here, what I can see is what are all the variables included within that data set that I just uploaded? What's the variable name? What's the alias? Is it an independent variable? Is it a dependent variable? What's the physical type? And also, what are the units? And the great thing with using multi-case for this is that all of this information is included within that JSON file. That file that I've exported from multi-case, I can bring it right into AI Model Builder here, and it's all automatically set. So there's no additional work needed on my side besides just reviewing what was automatically configured and tweaking some things if I choose to. I have the ability to change independence to dependence if I wanted to do that. I'm not going to do that in this case, but I have the ability to do that if I was interested in making those kinds of changes. So once I've reviewed the variables here, I can proceed to the clean data step. And what we have on the clean data step is the ability to view the data set in a little bit more detail using this table grid here, where along the columns I can see the different variables, and along the x-axis I can see the different case numbers. So I could scan through this and review some of the results. I also have the ability in multi-case to view similar types of reports if I wanted to do that kind of analysis in there. I have the ability to apply outlier detection if I want to as well at this stage. This can be useful if I'm using data sources other than simulation data. Since this is simulation data and it already is relatively clean without many outliers or anything like that that I want to remove, then I'm not going to enable it in this case, but it is useful if you're using other data sources. The next step is to proceed to the build model page and review the feed streams and the product streams that are coming through this individual hybrid model. And again, this is another place where the power of multi-case really comes through. All of this is automatically set within the AI model builder once I upload that multi-case file. So multi-case is able to tell us what are the feeds to my model, what are the products, what are the temperature, pressure, flow, composition, and all the other specifications that I need in order to build this reduced order model. And if you think back to some of the items that Sandeep was talking about previously, this isn't just a strictly data-driven model that we're building. We're also including that sort of first principle augmentation and some of those constraints from the real world, such as a mass balance. So it's important for us to have these types of variables for temperature, pressures, flows, compositions, and everything else so that we can ensure the model we're building is truly in mass balance and it's not violating any of these real-world constraints. So at this stage, I would simply review the information that multi-case had set. I could alter this if I chose to, of course, on any of these different streams. I could add different variables if I had perhaps some other variables included in my initial multi-case model, and I could make those kinds of changes before I actually create that model. Now, once I'm satisfied with that, I have all of my configurations set up. I would click on this Create Model button, and it would proceed to the Validate Model page once that model is built. Again, in the interest of time, I've already created this model, but I will show you all of the results that we can observe. So after clicking on that Create Model, I can now scroll through this and first look at all of these different parity plots for my individual case. And what these parity plots show me is along my x-axis, I can see the observed value, and along my y-axis, I can see the predicted value from the hybrid model. So of course, the closer I am to this 45-degree diagonal line, the more accurate my model is. And the higher my R-squared value, the more accurate my model is as well. So I could go through this process of observing these different graphs, looking at these different R-squared values, and I have a table down here to toggle different ones on or off, and I can get a general sense of what my model is predicting. Now, what happens if these results aren't great, or if the model I've built isn't very accurate? Well, there's a few different things I could try. First up, we have a few different parameters that you can play around with right on this Validate Model page. One of them is called the high order checkbox here. So what I can do is introduce higher order components for a particular variable. I could do this on one variable, two variables, or theoretically all of them if I wanted to. And what this attempts to do is really up the complexity of the model by introducing more high order components by trying and hopefully build a more accurate model as a result. So again, all I'd need to do is check this off for individual variables if I wanted to try to build that. It will take a minute or two to actually train that new model, so I've already done that. But you can see down here within this little window here, I have a V1 and I have a V2. And version 2 has introduced a higher order component for this particular variable down here. I just picked the mass fraction of water since previously it was around 0.8. And now with this new model, we're able to bring it up to about 0.88. And it's also improved the overall R-squared of my model as a result by introducing this higher order component. So that's one tool I have available to me to try improving the overall fit of this model. I can also change this test and train ratio and see if that has an overall impact on what my model is predicting. I also have the option of going back to clean data, altering some of my clean data parameters, or I could go back to the very start at multi-case and perhaps add additional variables, widen the range on a particular variable, the lower and upper bounds to get a wider sample. And there's a number of different things I could try. And you can see the overall process. I didn't show it live in this case, but the overall process of setting up this model is fairly quick. After you run those multi-case runs, which take a pretty short amount of time compared to running it locally without multi-case, all I need to do is import that data into AI Model Builder, proceed through some review steps, construct the model, and then view the underlying model at the end of that. So it's a pretty easy and a pretty intuitive process overall. Now, once I'm happy with these results, and I'm satisfied with what my model is predicting, the next step is to export this from the AI Model Builder and deploy it into HYSYS. So in order to do that, I would click on this little rocket ship icon on the side, and I choose where I want to deploy my hybrid model to. Now, in this case, we of course support our latest version, version 12, so we can deploy hybrid models into version 12, but we also offer some backwards compatibility as well. We could take this exact same hybrid model and deploy it into HYSYS version 10, as well as HYSYS version 11 through a HYSYS extension. So you have that option available to you as well. Now, after I've exported that model, I would come into HYSYS and I'd begin the process of using it within my flow sheet. So I've already set this up, but I'll show you what the process is for actually configuring this. What I would do is click on the models and streams here, and then the next thing I would do is look for my hybrid model unit operation. So I could either search for this or deploy this, or use it on the external model tab. And after I drop this on my flow sheet, you'll see that I need to change the directory and select where I have that individual hybrid model saved. After that's saved, I would use it and deploy it the same way I would use any other HYSYS unit operation. And I'll zoom in just on this section up here to show you what this looks like. So this is the model that I've just built within this HM-100 unit operation. And you'll see I can click on this, and I will use this the exact same way I would use any other sort of HYSYS unit operation. I would connect my feed streams, my product streams. I have different inputs perhaps depending upon the type of model. I can view the results if I have specific parameters in there, and I can see the stream results and integrate it within a flow sheet the same way I would integrate any other type of model. Now, I've already validated this model within the HYSYS case, or within the AI Model Builder, excuse me. So the next thing I could do is start to validate this within the HYSYS case and compare some of these hybrid model results with the rigorous HYSYS model results. So I could review, say, just as an example, I've included this stream, the C107 overhead stream down here. This table is representing the rigorous HYSYS results for the temperature, pressure, and flow composite molar flow calculations. Now, I can review these same results within the HYSYS stream up here for C107 overhead to see the temperature, pressure, and molar flow. And you can see they're nearly identical. I could then make a change into this case, say change my temperature from 35 to 40 degrees C. You can see the hybrid model solves pretty much instantaneously. And then I could make the same change in HYSYS. And this will take a little bit longer to converge, but it's a pretty small step change, so it doesn't take too long. But then I could view, again, the new predictions. We're still predicting the temperature and pressure at 101.4 in both cases by observing these two tables. And the molar flow is 19.91 in the hybrid model and 19.74 in the rigorous model. And, I could keep doing this activity, comparing different model results, comparing different stream results until I'm really happy and comfortable with what the hybrid model is predicting. So just to briefly recap what I just showed, we started first in multi-case. We generated all of the simulation data we needed to build our reduced order model. We then exported that data, brought that into the AI Model Builder, where we used that entire data set to build a reduced order model that, again, represents this entire section of the HYSYS flowsheet. We then created that model, validated that model, and exported it, and deployed it back into HYSYS, and used it in HYSYS the same way we would use any other HYSYS unit operation. So that really concludes the first of the demonstrations, and I'll switch back over to the slides now, and we can start the process of going through our next demo. So the next demo I'd like to share with you today is how we can build one of these reduced order models and deploy it into the planning world, using it specifically within Aspen PIMS AO. So the ultimate goal here is to build as accurate of a model as possible, to help increase our margins and also save time. So by doing this, we estimate there's a potential benefit of somewhere around 10 to 25% of a planning optimization benefit, which translates to around 3 to 15 cents per barrel typically. Through this intuitive and streamlined workflow, we can improve the overall time for building and updating these models by as much as 50%. And since it's a relatively streamlined, again, and intuitive and automated where possible workflow, this is really applicable to any type of user. So ultimately, we could look at how we could reduce consulting fees on these types of projects by up to a total of 75%. Now, the actual process of building one of these, which I'll show you in a minute, has been validated with a number of different companies. And I'm showing you one example here where we worked with a European energy multinational corporation. And the challenge they were trying to address was to build a more accurate and a more reliable planning model. And their current planning model had a number of missed opportunities using the conventional base delta LP models within PIMS. So our solution was to build this new reduced order model. And we could use that reduced order model and deploy it within PIMS-AO to have a more accurate model as a result, and also showcase some of the nonlinearities within our planning case. And we had an estimated savings here between, again, 3 and 15 cents per barrel, with a 50% improvement on time for model building and model updating. So the overall process for doing this is very, very similar to what I just showed you. Most of the differences will be highlighted on the deployment side of things. So we'll, of course, first start with the data definition and the data collection, again, using multicase. This is all based on an existing HYSYS simulation model. So we'll use that simulation model to generate all of the data that we need in order to build our hybrid model. We'll then take all of that data into our AI model builder, where we do that process again of data conditioning, data cleaning, model building, and final model validation. We can then deploy that model down into PIMS-AO. And we have a very simple and a very streamlined workflow for embedding that right within an existing PIMS worksheet. So the case that I'm going to show you is a case where we have a rigorous FCC model in HYSYS, and we're going to build a reduced order model that represents that rigorous FCC model. And we're going to deploy that hybrid model, or that reduced order hybrid model, within Aspen PIMS-AO. So the demonstration that I'm going to show you is going to focus exclusively on the deployment step into PIMS-AO. That overall workflow for data collection, data generation, model building, all through multicase and eventually AI model builder is exactly the same. So I'm only going to highlight the end portion where we're looking to actually use this model within PIMS. So let me share my screen again, and we'll transition over to this PIMS model. Okay, so what I'm showing you here is the base run for this PIMS model, where I ran this using only those base delta LP models. And what we're seeing here is I've ran a number of different cases 16 through 23. Right now I have one in feasibility, and what I'm seeing on this y-axis is my profit in thousands of dollars per day. And you can see by observing this that we see a linear response across these different cases, with a maximum right now of $1,119 per day. So keep these numbers in mind and keep this response in mind as we look at what happens once we integrate this reduced order model. So the actual process of embedding this hybrid model and using it within PIMS has been greatly improved with our version 12 release. So the way that we do this is we first go to the external model tab within PIMS, and we'll add this reduced order model as an external model to my PIMS case. So I'll go ahead and right-click on this, and we'll add our external model, and I'll select hybrid model as the model type from this new form. I'll then browse, and we'll go to where I have saved that hybrid model that I built. So when we build the hybrid model for planning, we deploy it using this XLP format that can be easily deployed within PIMS-AO. So I'll go ahead and click on that, click on OK, and now we have our hybrid model within PIMS. The next thing I need to do is to create a PIMS submodel container so that it's easily ingested by this PIMS model. So I'll go ahead and click on that, create that new one, and I'll just overwrite that for the time being. So now I have my reduced order model added as an external model within PIMS-AO, and I've created a submodel container for it. The next step is I need to take that hybrid model and tell PIMS which unit or which portion of the process it corresponds to. In this case, I'm going to attach it to the SCCU unit here. So I'll go ahead and click on this and click on Add. And then here is that PIMS container submodel that I just created. So I'll click on Open. This will take a few seconds to recognize it. And I'll need to just select the first sheet within that Excel file there that we've created that reduced order model container for. I'll then go ahead and suppress that original base delta LP submodel and then keep just this hybrid model running. Now I'll run these models again, and what you'll see is really the change in response from using that original base delta model and this new reduced order hybrid model. And what you'll find is the overall profit prediction will be higher, and on top of that, the nonlinear response will be observed in this graph over here, showing the cases and the profit per thousands of dollars per day. So I'll give this just a few seconds to complete the run here. It shouldn't take more than another 10 to 15 seconds. Okay. And you can already see as these results are coming in, I know this text is a little bit small, but you can already see within case 19, for instance, we're producing a higher all profit already at 1,221 thousands of dollars per day. Previously, the highest was 1,119. Now, we just have one more case that needs to complete, and there we go. And now we can see that previously we had an infeasibility at case 16 for that set of inputs. That result is now feasible using this new reduced order hybrid model. And the overall trend we can observe here is showing that nonlinear behavior that we would expect. So this is actually predicting that overcracking peak within that unit, and we're able to observe that within our planning model here. Now, we've predicted that nonlinearity, and we've also predicted an overall higher profit prediction as a result of this new improved reduced order model. And again, recall previously we produced about 1,119 thousands of dollars per day. Now we have a maximum at case 21 at 1,238 thousands of dollars per day. So just to recap what we've done, I didn't show the beginning portion, but we started with first generating this data in multi-case. We then brought all of that data into our AI model builder to build this reduced order hybrid model. And then we took that reduced order hybrid model and we deployed it within PIMS. And you saw how easy and how simple it was to deploy that and run it all within PIMS. And as a result, we're able to observe some of these nonlinearities and also produce a higher overall profit prediction as a result. So I'll transition back to the slides now. And the next thing I'd like to cover is just that second type of hybrid model that Sandeep was covering at the beginning. So we talked a lot about the reduced order hybrid model, and I showed you two different demonstrations of how we could use these reduced order hybrid models within the simulation world as well as the planning world. Now, the next one I want to talk about for a couple of minutes is this AI-driven hybrid model. And really the main difference here is that we're still building this hybrid model, but our data sources may be different. And we could be looking at perhaps using lab data, plant data, field data, simulation data, or really a combination of all of them to build this hybrid model. And one of the differences that we're doing here is that in many cases, we're actually building a brand new unit operation. So we can take all of this data that we ingest into the AI model builder to build, say, a brand new membrane unit operation, or perhaps other types of unit operations that don't exist currently within HYSYS. We can use this AI model builder technology to build these brand new unit operations in a very streamlined and in a very easy way and deploy them down into our simulation tools and use them the exact same way we would use any other type of unit operation. It would look very similar to what I just showed you for the reduced order model case. Now, we've also validated this technology with a number of different companies, and one I'd like to highlight here was a national oil company that we worked with in the Middle East. And the challenge that they were facing was they were having difficulty meeting some of these anode grade pet coke specifications. And they didn't really have a great model in order to meet these specifications. And the effort required to build one of these very customized models had a super high cost, and there was a significant amount of effort required in order to build this customized model. So the solution that we arrived at was building one of these AI-driven hybrid models for a delayed coker and a coke calcination unit that we could deploy right back into HYSYS. So the user didn't have to go through this long and arduous process of building this very customized model. Instead, we could use this AI model builder technology, specifically focusing on this AI-driven hybrid model, to build this custom model and deploy it right inside of HYSYS. And as a result, we were able to gain greater visibility for improving the coking operation strategy and get a more complete picture for process optimization. So that concludes the demonstration portion of our presentation today. I'll now turn over back to Sandeep, who will go through a quick summary and we'll wrap up with Q&A. So over to you, Sandeep.
Thank you, Alex. Now, as Alex mentioned before, many major energy companies worldwide have already tested and approved this new revolutionary technology. Here are just two examples of two leading energy companies from two different parts of the world. The Indian energy and petrochemical giant Reliance found this hybrid modeling technology as a major advancement in the field of chemical engineering. They see it as a true game changer in process engineering. The Italian multinational energy company Ceres found that the Aspen hybrid models provides a new and very efficient approach for generation of nonlinear planning models for updating their planning solutions. Now, in summary, the Aspen hybrid models are a major advancement in the field of chemical engineering. It does so by truly democratizing the application of AI. They enable users to model equipment and processes that could not be modeled before using conventional simulation technology, thereby improving and optimizing processes. They enable engineers of all skill levels to easily create and sustain process models. They enable development of flexible digital twins that can be deployed to multiple and diverse teams in an energy company. Now, what are the next steps you could take to get started using the new Aspen hybrid models? We've made available a host of materials to get you started using these capabilities. We have listed some of those materials here. These are hyperlinked, and you may access them by clicking on them when we distribute this deck after this webinar. You can access many more such materials by visiting our website or our customer support site. If you need any further help, please feel free to contact your Aspen Tech representative. Now, we will open up for the Q&A session. Please send us your questions by typing them in the Q&A panel, which you'll find at the bottom right of your WebEx window. Please also make sure that you submit the questions to all panelists. So the first question, I'll post this to you, Alex. The question is this: if the hybrid models use AI, will they not require large amounts of operation data to train the AI?
Mm-hmm. Yeah, so really the guidance I would have is to provide as much data as you possibly can in order to build an accurate model. Now, one thing that we're doing to help improve cases where there's not a significant amount of data is actually introduce more parameters or more variables into the model to try to build a stronger or more accurate model as a result. To expand on that a little bit further, that's really in the AI-driven side of things, where we can really have you provide information on what you're actually trying to model or what you're trying to represent. And you can include phenomena such as mass transfer or pressure drop. And with that knowledge, we can calculate additional variables based on what you supply to try to introduce more context or try to introduce more overall variable to a limited data set to build, again, that stronger model as a result. So to your initial question, try to provide as much data as you possibly can. And of course, the data is hopefully as variable and as non-steady state as well as it could possibly be. But we are doing some work to enable supplementing smaller data sets to build in greater accuracy as a result.
Thank you, Alex. The next question, I'll post this to Shinoj Bhaskar, who's the product manager for Aspen PIMS solution. So the question is this, Shinoj: can AI-driven hybrid models also be used to optimize production planning, specifically for batch distillation processes?
Thank you, Sandeep. That's a very good question. So the answer is yes. The AI-driven models can be used for doing the production planning process. Although I should also state that we would like to understand what is the production planning process that you are using, the kind of tools, right? And we do support that within all the Aspen suite of products, as Alex has demonstrated. Thank you.
Thank you, Shinoj. So I'll pose the next question to Erika Belmont, who's the product manager for Aspen HYSYS upstream midstream. Erika, the question is this: does the process have to be at steady state when you run online, just like RTO?
Yeah, currently this AI model builder is supporting steady state models, so it has to be a steady state. But in the future, we want to expand the capability so we can support dynamics models.
Thank you, Erika. I'll pose this next question to you, Alex. The question is this: can you explain further on the predicted versus observed variables accuracy and predictability? Is the data being observed taken from the simulated HYSYS results? What is the AI model comparing it to determine accuracy?
Yep, good question. So what that graph is showing is, again, the predicted versus the observed. And the predicted in this case is the value that's coming out of the hybrid model. So for a given set of inputs, what is the hybrid model predicting? And then we're able to compare that prediction to what the data actually says. So in that case, we compare the prediction of the hybrid model to what HYSYS calculated. Now we have two different things that we report in there. There's the predictability and there's also the accuracy. And those are represented by two different variables, an R squared and a Q squared. Now what the R squared represents is really how well your data matches to your training set. And then the Q squared is how well your data matches to your test set. So when we get a large data set coming into the AI model builder, we randomly segment it into two different portions. There's a training set and a test set. A training set is what we use to initially build that model and train it against all of the results from HYSYS. And the test set is what we use to get an idea of how well that model is predicting different variables with, again, this randomly chosen test set of data. We separate them to make sure that there's no duplication between, so we're not, training and testing on the exact same data set. And then we're just reporting these different metrics as accuracy and predictability to segment between what we used for training, what we used for testing, and how accurate is it for both of those different criteria.
Thank you, Alex. Please give us a minute as we go through. We have a number of questions, so we're going through one by one. So, please bear with us for a second. The next question, I'll pose this to Ankita Mangal, who's the product manager for Aspen HYSYS for the refining industry. So the question to you, Ankita, is this: so the implementation of such application, is it done by Aspen people, or do you train engineers in refineries so that they can do it themselves?
Thanks, Sandeep. This is a very interesting question. We have Aspen Tech Services Group who can help with creating hybrid models, but the way these hybrid models are designed and developed and the technology that is used is in such a fashion so that users can build it themselves. And these models are, the creation, deployment, development can be done by really anybody. So you don't have to be a data scientist to build these models and use them. It could be used by anybody, a process engineer, planner, control engineer. So you don't have to be a data scientist. So it's extremely easy to create, as Alex demonstrated, and also to deploy and sustain the models. Thank you, Sandeep.
Thank you, Ankita. The next question, I'll pose this to Ajay Lakshmanan, who is the product manager for the Aspen HYSYS family of products. Ajay, the question is this: what do you mean by Aspen Tech's domain knowledge with regard to the hybrid modeling presentation given today?
Sure, Sandeep. So Aspen Tech has delivered best-in-class software solutions with first principles-based models for the past 4 decades. in the oil and gas industry, petroleum refining, chemicals industry, and so on. This is what we mean by our domain knowledge. We have improved and perfected our models over time, and we can use a lot of these relationships, as Alex Rayo mentioned, for example, mass balance and other constraints, to augment the information available in the data, operations data, to create these AI-driven hybrid models, as well as hybrid reduced order models, if you will. So this is what we mean when we say domain knowledge, incorporating our expertise along with machine learning techniques.
Thank you, Ajay. I'll pose the next question to Alex. The question is this. When you create all of the model runs, do you perform a designed experiment to maximize the usable space?
Yep, great question. So what we're doing is, after the user has defined all of the independent variables, we set a default for the lower and upper bounds at -20% and +20% that you can, of course, change. But we take all of that information for the different independent variables, the lower bounds, the upper bounds, and we sequence all of that using a technique called Sobol sampling or Sobol sequencing. And what that is really an intelligent design of experiments to make sure that these cases are all sequenced in a very intelligent and a very efficient manner, to make sure that we're really getting adequate representation within the range that I've defined and recovering all of those different points that may be important to make sure that as I'm using this reduced order model, there's not any blank spots in there for those different ranges I defined. So the answer to your question is yes, we are using an intelligent design of experiments. In this case, we're using a technique called Sobol sampling, and that's based upon what you have as your base values and what you set as your lower bounds and your upper bounds.
Thank you, Alex. The next question is also for you. Are there any indicators to prevent overfitting, or do we need to manually check the results observed by the model? Alex?
Good question. So right now, there's no indicators that mention anything about overfitting. There's nothing in the tool right now to really indicate that. That's certainly something we could look to add in the future. So we'll have to get back to you on that in terms of what we can do to ensure that if there is overfitting occurring, we're flagging it. But right now, there's no sort of indication in the tool that indicates that.
Thank you, Alex. I'll post this final question to Ankita Mangal, Product Manager, Aspen HYSYS Refining. Ankita, the question is this. Can hybrid model replace the reactors that are hard to be simulated?
Sure. Thanks for the question, Sandeep. Yes, hybrid models can be replaced to simulate reactors that are difficult to be simulated using conventional techniques. So as Alex kind of mentioned, if there are models, if there are like processes for which we do not have existing technologies, we can model that. If there are complex reaction networks, kinetics, unknown mechanisms, hybrid models can be used to develop models for those. And any processes for which we do not have out-of-the-box model available in any of the simulators. And basically the idea is that if you have a lot of historical data, so the case study that Alex demonstrated for the coke calciner unit, the customer didn't have any out-of-the-box model available. So we started with historical data, conditioned that data, and then kind of augment it using engineering calculations, impose constraints, embed the domain knowledge, and create an accurate hybrid model. So the answer is yes, the technology allows to build models for processes which are kind of difficult to simulate, the technology is designed in a fashion that it's quickly, extremely easy to create such models. Data cleaning in data constraints, building engineering calculations and embedding domain knowledge, all the process from start to end is extremely easy. So any user can do that. Yeah. Sandeep, over to you.
Thank you, Ankita. With that, we will wind up this webinar session. We received a lot of questions which we were not able to take up today due to time limitations. So we will send out our response via email. Thank you so much for attending this presentation and have a good rest of the day.